Hi, Doctor. We are from Group 4, and our group assignment is about deep reinforcement learning for autonomous map-less navigation of a flying robot. And I'm DSC 2209260 Jihan. And first, I will introduce the background. Macro aerial vehicles are now widely used in tasks such as aerial delivery, hazardous area inspection, search and rescue, and environmental monitoring. To perform these missions, they need reliable autonomous navigation, meaning they just sense the environment, plan safe paths, avoid obstacles, and reach targets without human control. Conventional map-based navigation builds a map, localizes within it, and then plans a path. But this relies heavily on having an accurate and stable map. For flying robots operating in complex 3D spaces with tight areas and moving obstacles, creating and maintaining such maps is difficult and often unrealistic. So this leads to mapless navigation, where the MAV avoids the need for a pre-built global map and makes decisions directly from onboard sensors. Deep reinforcement learning supports this by learning end-to-end policy that maps sensor observations directly to actions. So the motivation is clear. Why mapless navigation is needed? Mapless navigation enables fast real-time decision-making from sensors. It works well in unknown or high-risk environments where maps are unavailable, and it fits the limited computational capacity of micro aerial vehicles. And why deep reinforcement learning? DRL strengthens this approach because it learns navigation strategies directly from sensor inputs, generalizes well to unseen environments, and naturally develops both obstacle avoidance and goal-seeking behaviors. It also fills an important research gap, as most mapless navigation studies focus on ground robots, with far fewer validating DRL on real MABS. And then pass to my teammates.
I will talk about what challenges this work faces. First, mapless navigation using local LiDAR and depth. Second, sim to real gap. Third, limited onboard compute on the Jetson TX2. Fourth, high dimensional sensor inputs. Fifth, safety during training. And balancing exploration and exploitation in DRL without crashing the drone.
Now, let me introduce the methodology. Next, the first part is robot platform and system overview. Our system consists of 3 layers. The hardware platform includes Pixel flight controller, Jetson TX2 computing unit, RGBD camera, and LiDAR. In the architecture, sensor data is processed by the DRL model on Jetson TX2, then outputs velocity commands to Pixel for motor control. The software stack uses ROS middleware, TensorFlow for training, and Gateball for simulation. This is a mapless autonomous navigation system. Next slide. The system uses smart model switching. When no obstacle exists within 2 meters, mission flight mode activates, flying directly to target points. When obstacles appear within 2 meters, it switches to DQN flight mode, where the deep learning network avoids obstacles. The guidance system on the right is the core. It combines both modes using weight 1 and weight 2. When distance is less than 2 meters, weight 1 equals 1 and weight 2 equals to 0, giving DQN full control. When distance exceeds 2 meters, weight 1 equals to 0 and weight 2 equals to 1, switching to mission mode. A human pilot can take control anytime. Next slide. The collision awareness module is the core of sensor fusion with 3 steps. Step 1, standardization. Both LiDAR and RGBD depth images become 90 × 90 binary images. This simplifies network inputs and reduces the gap between simulation and real world. Step 2, temporal stacking. 2 frames from each sensor are combined, providing motion information. Step 3, outputs a 90 × 90 × 4 observation passed to the DQN network. This design uses multiple sensors together, detecting both small and distant obstacles.
Hi, I'm Meng Xiao. Let me continue with our part. As mentioned, the CAM produces a very large observation space. Because it is high dimensional, a Q table would be impossible to store or update efficiently. So the Q function is approximated using a deep CNN instead of tabular Q learning. Moving on to the action space, the agent has three discrete actions: turn left, turn right, and move forward. Therefore, the DQN outputs three Q values, one corresponding to each action. Next. Next, the authors use a CNN consisting of two convolutional layers, radio activation, max pooling, and a final fully connected layer that outputs the three Q values. This allows the agent to interpret the data map in a more abstract and compact way. The reward function encourages safe forward movement. If the minimum distance is more than 2 meters, moving forward gives a high reward and turning gives a small penalty. If the distance is below 2 meters, the agent gets a large penalty and the episode ends. Next, to stabilize learning, the target network is used to compute the target Q value. This network updates slowly, preventing the learning target from shifting too fast and avoiding training divergence. In addition, the system uses experience replay. A replay buffer stores past transitions, and each training step samples a mini batch of 32 examples. This breaks temporal correlations and make gradient updates smoother and more stable. During training, epsilon decays from 1 to 0.1, so the agent explores more at the beginning and gradually shifts to exploiting better actions. Next. Putting everything together, this is the overall training workflow. By combining the CAM with deep Q-learning, CAM function approximation, target network, and epsilon greedy exploration, the system can operate effectively in high-dimensional environments. Next, I will pass it to my teammate.
Moving on to experimental outcomes. First, training details and learning behavior. We train separate indoor environment B and outdoor, which is environment A, policies in Gazebo with PX4 SITL for 2000 episodes. The learning curves show that the outdoor reward converges faster and higher, around 73, while indoor converges lower, around 49. Next, simulation testing, or sim-to-sim generalization. We test on the seen training environments A and B and unseen C and D for 10 episodes each. The outdoor policy scores about 95 in A and 85 in C, while indoor B and D average around 60. Then we compare our method with a classic potential field algorithm in 3 scenarios. In scenario 1, a structured indoor light map, the potential field baseline drives into the central obstacle, while the DQN path bends around it and stays smooth. In scenario 2, a corridor with randomly placed obstacles. Both methods look similar at first, but near the critical point, the potential field crushes, whereas the DQN policy safely reaches the end. In scenario 3, a forest-like open space with many trees, the potential field method gets stuck in the clutter, but the DQN policy still threads a path through and exit the environment. Finally, we show fully autonomous simulated missions. For outdoors, mission mode heads towards a target, and DQN mode takes over when obstacles come within 2 meters. For indoors, the drone visits targets T1 to T3 and returns without collisions. Thank you. I'll pass it to my teammate.
Next, Sim2Real and a real indoor corridor test was conducted using only the DQN mode with no map. The drone takes off and moves forward, trying to stay in free space, and the real depth and LiDAR images closely match the simulated binary views, where the walls and obstacles are the white regions, while the empty space is the black region. Next. The graph here shows that the accumulated reward stays positive and peaks near the corridor exit, which happens around episodes 800 to 1000, showing a safe traversal without collisions. Next. In scenario 2, we use an L-shaped indoor corridor with a standing person as an obstacle. The drone flies autonomously at 0.6 meters per second, turning to avoid both the walls and the person. Next. So this is a graph that shows the DQN control performance. On the right, red is desired and blue is actual. Yaw angle is its heading direction, while yaw rate is how fast it turns. So these curves match closely, showing the controller follows the DQN commands and the drone moves stably through the corridor. Next. In scenario 3, the system is tested outdoors in a forest trail, with randomly placed trees as static obstacles and a walking person as a dynamic obstacle. So the mission pattern follows the pre-planned shortest path between home and the target, and whenever an obstacle appears ahead, the AV automatically switches to DQN mode to avoid it, then returns to mission mode. Next. So in here, the drone actually reaches the target and comes back to the start in about 115 seconds without any collisions, while its heading and forward speed closely track the desired commands. Next. We can see here that the depth and LiDAR images clearly shows the trees as wide obstacle regions, so the sensor representation still works well outdoors. Next. As for the personal insights, next. From this paper, we found that mapless navigation is actually practical, and the drone can fly in unknown indoor and outdoor spaces without a 3D map just by turning raw LiDAR and depth into velocity commands. It also shows that deep reinforcement learning can replace handcrafted navigation rules, learning collision-free behavior purely from rewards. Scientifically, it proves that a deep reinforcement learning plus sensor fusion policy can beat a classical potential field method and still generalize across new environments and from simulation to the real world. Next. So this is the research paper that we use for our presentation. Next. And that is all for our presentation. We hope it was insightful. Thank you.